Okay, so let's continue with the last type of clustering that we're going to be seeing today, which is mixture models clustering. And I'd like to go back a little bit to the k-means algorithm that I explained earlier today. I remember that k-means basically what it does is that it has a set of data points and it assigns each data point to a cluster, okay, until the distance between points and cluster centroids is minimized, and we end, the point to cluster distribution. The reason why I'm mentioning this is because I'd like to emphasize the fact that k-means assigns each data point to just one cluster. Okay, so for example, if we were classifying individuals into groups, individual 1 could be of cluster 1, individual 2 would be a member of cluster 2, individual 3 would be a member of cluster 2, and so on. Okay, however, oftentimes this is not the actual setting, and in fact, individuals might be part of different clusters or could be potentially assigned to different clusters. And so we'd be talking more of kind of a soft clustering where a given individual could be part of different clusters with a certain probability. So for example, the probability that individual 1 is part of cluster 1 is really low, is 0.1, but it's highly probable that individual 1 is a member of either cluster 2 or 3, okay, because the probabilities are very similar. Whereas, for example, if we look at the individual 1, clearly that individual should be a member of cluster 3 because the probability is really high. And so mixture models are basically an attempt of moving more towards this type of soft clustering, okay? And so, they belong to a family of probabilistic models that basically move away from assigning each point to a unique cluster as opposed to basically looking into soft approaches where a given point can belong to multiple clusters with different degrees of membership. And so Gaussian mixture model is just one example of this type of soft assignment. Okay, if you think about Gaussian distributions, so if you have a set of data points, you could explain how those data points behave or the distribution of those data points via multiple Gaussian models. So for example, what I'm showing here, imagine that data that we have collected is actually data from two different classes, and we can clearly see here that we have two different Gaussian distributions. Okay, so in this case, the data points could be members of one or the other or both Gaussian distributions at different probability level. So then the idea behind a Gaussian mixture model is that we know, we assume that the data has been generated from a multimodal distribution. That's it. We know that our data originates from different groups or subgroups of data from different Gaussian distributions. And so can we find a way of representing this multimodal distribution as a mixture of unimodal distributions? Like, can we disentangle what are the different Gaussian distributions that could potentially explain the data set that we have collected, right? If we can do that, then we can basically use each Gaussian distribution as one of the clusters that we are trying to separate, and then we can label each of the data samples in our data set as being of one Gaussian model or the other, that's it as being of one cluster or the other. So what you can see in this representation here at the bottom of the slide is that we have a set of data points, right? We assume that all those data points xn, and n means that each data point has multiple features, has been generated by a multimodal distribution, and then what we want to do in the part B, we want to be able to disentangle the different Gaussian distributions that we have, and then for any given point in our data set, we'll be able to assign a label, Zn, to each of the data points that we have, and that label might be one of the different Gaussian distributions that we are considering. Okay, so again, the underlying assumption is that we have multiple Gaussian distributions that can explain our data. We try to identify those Gaussian distributions, and then we assign points to each of those distributions, and those are going to be our clusters. Before I formally explain, Gaussian mixture models, let me just review a few concepts that are important. So again, everybody on board, Gaussian distributions explain the data data changes based on an average value and on a spread, okay? And basically the probability density function for a Gaussian distribution can be explained based on the average and the spread and the standard deviation, okay? And so the probability of a given point having been generated by this Gaussian distribution can be explained with that formula. Similarly, we might also be interested in understanding likelihood, right? And so likelihood would answer the question about which Gaussian distribution is more likely to have generated the data that we have, right? And again, this is something that we are interested in doing because we want to understand what Gaussian distribution is explaining better some of the points that we have in our distributions to be able to assign them to clusters. And so likelihood, basically, to compute the likelihood, what we need to do is, for all this data set, for the points that we have, we basically need to multiply the probabilities of those points having been generated by a specific Gaussian or another, okay? And so basically the formula that you have down there is the product of, all the different probabilities for each of the points that we have, given that we are assuming a specific average and spread. Okay, and remember that if we want to compute the log likelihood, which is what I'm going to be talking about, if you log that product, then it's transformed into a summation. And then a third important thing is that generally we're going to be talking about data points that have multiple features, multiple variables. Remember that generally in our problems we consider multiple independent features, and so it's important to understand that then in that case, the multivariate Gaussian distribution, the spread has to be represented as the covariance matrix, and the covariance matrix just explains how features vary with respect to each other, okay? And then the mean is going to be a vector with as many values as independent features. But the formula is exactly the same. The only thing that changes is the covariance. And then in terms of log likelihood, as I was saying before, this is expressed as a summation, because when you log on a product, it's basically the sum of its elements. Okay, and so if we go back to the original question that we are trying to do here, is that we want to understand if we can actually identify the different Gaussian distributions that could be explaining subcomponents of our data, because those could be then our clusters. And a way to formalize this idea is to basically consider a mixture of k Gaussian components as follows. So we can explain the probability of a given point happening in our data set can be explained as the probability of a given cluster K happening multiplied by the probability of, given that we have that cluster, of the point Xn being a member of that cluster, okay? And so in other words, we can express this as a linear combination of different Gaussian distributions, okay? Meaning that for a given point, that point can be part of Gaussian 1 with a given mixture proportion, can be part of Gaussian 2 with a given mixture proportion, and so on. Okay, so in other words, this is a soft clustering that I was referring to at the beginning of the class. Okay, so if we have, imagine for example for the plot below, if we have a point that's kind of between the red lines and the green lines, then that point can be expressed as, being either red or green, as being part of either the red Gaussian distribution or the green Gaussian distribution with different probabilities, okay? And that mixture proportion is nothing else than the number of points that we have for that specific cluster over all the points that we have in our data set. And so, assuming that representation, that mixture of different k Gaussian components that could be our k clusters, then what this model is describing is that each data point in reality can be generated as two steps. The first step could be flipping a k-sided die, being k the number of clusters that we are considering, and being pi k basically the probability for that clustering being selected. Okay, again, for a given point, the probability of being a member of one cluster or the other is going to be sometimes higher, sometimes lower, right? And so there's going to be definitely one of those sites in your die that's going to have a higher probability, and so that's the cluster that's going to be selected. And then given that cluster, we generate the value for those data points using the Gaussian distribution. So basically using the average, the average and the covariance matrix for that specific cluster. So now how do we learn the Gaussian mixture model? In other words, how is the training done when you are running a software package? So basically we need to learn what we call the mixture parameters, right? So we need to learn what's the average for each cluster, what's the mean for each cluster, sorry, what's the covariance matrix for each cluster, and then what's the mixture proportion for each cluster. And, assuming that we are considering k different clusters. And so the way we do this, basically to compute that set of Gaussians with all the corresponding parameters, another way of putting it is that we need to compute the set of Gaussians that maximizes the log likelihood of the data that we have observed, given, the parameters. And so in this case, it's important to understand that we don't have all the values that we need to be able to compute that, because there's a latent variable in there. In fact, we observe all the points, but we don't observe the cluster labels, right? I mean, the xi's, which are the data, are observed, by the c's, which are the cluster labels, are not observed, okay? And so when we want to maximize the log likelihood, okay, which we can formalize as something like that, basically a summation of the log of, the probability of a given point being a member of a given cluster, assuming a specific mixture variables like, like a specific mean and a specific covariance matrix, right? I mean, to compute that formalization of, the maximum likelihood is extremely difficult, mostly because, again, there's a latent variable c that we don't know anything about. Okay, and so we cannot basically solve this, and then what we do is that we take an optimization route and we use expectation maximization to look for, the best distribution of the mixture parameters that we are looking for, given the data set that we have. And so at a high level, the expectation maximization algorithm, what it's doing is that, we start with randomly mixture parameters. So we start with random means for each cluster. We start with random covariance matrices. We start with random mixture proportions for each cluster. And we basically, what we do in the expectation step is that we compute the probability of a given sample being member of one of the k clusters, assuming specific mixture parameters, right? And then once we compute that, we can basically impute the labels for each of the data points. And once we do that, we can go back again to the maximization step, where we will be recomputing the mean, the covariance, and the mixture proportion. Okay, recomputed those values, we go again to the expectation step, we compute the probability of each point being part of each of the different k clusters we are considering, assign labels, go back to maximization, and we continue this until we converge, meaning until the data points don't change from one cluster to another anymore. More formally speaking, I mean, what's going on behind, what's the math behind of these soft clustering or soft k-means? So basically in the expectation step, what we do is that we compute the probability of given an x point, what's the probability of that point being a member of one of the clusters k that we are considering, right? Assuming that we have a given mean and a given covariance. And then once we compute that for all the different clusters that we have. And then during the maximization, what we do is that we recompute those mixture parameters. So we recompute again the mixture proportion, the pi k, based on the number of points that we have assigned to each cluster. We recompute again the mean based on, the values that we have and the probabilities that we have. And we recompute again the covariance matrix. And that expectation maximization that I showed here highly probably reminded you of k-means, right? And again, the main difference between mixture models or Gaussian mixture models and k-means is just that the assignment is soft versus hard, right? So in the case of k-means, we are assigning a sample to one cluster based on distance, right? Whereas in this case, in the case of the Gaussian mixture models, we're exploring what are the probabilities of each point being a member of the different clusters we're considering, and we're basically assigning the label for the largest probability. But it's very similar, right? I mean, we originally we assumed that we had like randomly assigned centroids, and then basically we assign points to those clusters based on distance, and we recompute again the centroids for the clusters, and we do this until we converge to a given value. It's again same idea, but in the case of Gaussian mixture models, it's based on probabilistic approaches. And so this is just an example of how the Gaussian mixture model works to identify or to basically separate, these two data sets that we have. I mean, they're in green, but basically we have these two data sets that we want to separate with two different classes that we want to separate. And so we start with a randomly assigned centroid and covariance matrix for each of the clusters that we are considering, in this case, two clusters. And what we basically do is that we go through the expectation maximization loop. Okay, so originally the box labeled as C, in that box basically those are the random guesses that we are doing for the clusters, which are absolutely wrong. And then what we do in the basically expectation step, what we do is that we compute the probability of the points being part of one of these two clusters, and then we assign them, and then we recompute again in step D. In box D, we recompute again, in the maximization step, the mixture parameters, and we compute again the probabilities, and so on and so on and so forth, until, as you can see in the L equals 12, the points have finally been separated, meaning that we have identified means and a covariance matrix for each cluster that maximizes the probability of the points being members of those two clusters. And in fact, we are able to separate the points in that manner and identify the two clusters that we set out to identify. And let me finalize. I mean, if you are interested in, getting more details about this type of mixture model clustering, Gaussian mixture models, and about how expectation maximization is run, you can also check this paper.